The third and final example is called the solenoid. The solenoid is simply a long segment of wire that's been wrapped many times around some core. In the examples that you saw in class, it was simply an air core solenoid. But of course, in ways that you might expect, if you made the core iron or something highly magnetizable, you could make the solenoid much more powerful. Just as I do in the video about the toroid, I'm going to draw a cross-sectional view below here so we can get a look at what sort of enclosed currents we're dealing with. So if I slice the solenoid this way, then the cross-sectional view gives us a bunch of wires that are carrying current out of the page up here and wires that are carrying current into the page down here. I'm going to draw this diagram a couple times. The first time I'm going to draw all over it just to show you what goes on outside of the solenoid. If we start by looking at the front edges of the wires, the ones that are closest to you and me, then we can see that these wires are all carrying current in the downward direction. If we then use the right-hand rule, point our thumbs downward in the direction of those currents, then we can already sort of get an intuitive feel that the magnetic field inside the solenoid is going to point to the right. Because all magnetic field lines have to be loops, then taking these rightward facing field lines kind of leads us to conclude that they must loop around like this somehow. If we choose an Amperian loop, I'll go ahead and make it a rectangle since it kind of matches the rectangular cross-section. If I make a rectangular Amperian loop, let's just say it looks like this. You can see fairly quickly that such a loop is going to enclose just as many out of the pages as it does into the pages. And it's going to enclose just as many downs on the front end as it would ups on the back end. So no matter which way you were to orient this rectangular loop, or really a loop of any shape, you'll see that this thing the hand-wavy argument that I made about the toroid doesn't really apply here. I can't really use this argument. What we can do instead is look at the top and bottom rectangles and see that for the top part of the rectangle, ds points in the rightward direction, whereas the magnetic field line points this way. On the other hand, for the bottom part of the rectangular loop, ds points to the left, and the magnetic field still points to the left. So B dotted with ds would give you a negative number here, B dotted with ds would give you a positive number here, and so those two contributions would cancel each other out. These two segments of the rectangle run perpendicular to the magnetic field lines, so B dot ds would be 0 because of that perpendicularity. Similarly, if we make our loop live inside entirely the solenoid And if we chose our path to go like the same clockwise direction that I chose here, then you'll see that once again, because all of the magnetic field lines are pointing to the right inside of the solenoid, then for the upper part of the loop, you would get a positive dot product. For the bottom part of the loop, you'd get a negative dot product. I've already kind of explained to some degree why the field is more or less uniform inside here. So you get no solution here either. Again, this is not because the magnetic field is zero. It clearly isn't. It's because our choice of Amperian loop didn't take advantage of the geometry of the setup to give us any sort of answer that made sense. So what ends up being the solution is that you make your Amperian loop sort of live half in and half out of the solenoid. We can once again choose a clockwise loop, and this allows us to kind of take advantage of some interesting geometry stuff here. Let's take these one at a time. This is kind of a crude sketch of what's going on. But even if you take into account that the magnetic field lines may not be entirely perpendicular to these two segments, even if there is a slight upward or downward component, you notice that the ds runs in opposite directions for A and C, so the B dot ds cancels for both of these guys here. As for B, this is a little bit of a cheat, but if I just kind of let B's distance away from the solenoid start to get really large, then the magnetic field starts to get really, really weak out there anyway. So even if there were a major contribution to the magnetic circulation inside this rectangular loop, we can kind of just approximate that the contribution from B is negligible. And even if it weren't negligible, it would simply reduce the circulation a little bit from what's found inside there. So although you could say there is a small contribution from the segment of the rectangular loop for part B, it's not going to be all that big if we start to let B get far away from the loop, because as I mentioned before, this solenoid field gets weak as you get away from it. And you yourselves measured for the slinky that the field gets very weak outside the slinky. That leaves segment D as the only segment that really makes a meaningful contribution to the magnetic circulation integral of B dot ds. And that ends up looking rather simple. We can say that the wire segment has some length, I don't know, let's call it L. And so integral of B dot ds along that path only, which is why I didn't write the little circle symbol, simply becomes B multiplied by L. We can do that because B points in the rightward direction inside the solenoid, ds points along that direction, and when you add up all those B dot ds's, you simply get B times L. Now, how about the enclosed current? Notice that unlike the toroid, we can't simply say that there is n number of turns, because the solenoid could be infinite for all we know. In fact, these approximations work much better if you make the solenoid infinitely long. That way, in a certain way of arguing about it, these loops don't really ever close, so there's no field here anyway. At any rate, you want to think about, for some length L, how many of these things are you enclosing? Well, really all you can say is that for every 1 meter of solenoid that you have included in your loop, there's going to be some countable number of turns within that meter. So we simply assume n turns per meter. Therefore, I enclosed is simply n that has units of turns per meter times I, the current in each one of the turns, multiplied by L, the number of meters that you decided to make the width of your rectangular Amperian loop. A couple of things to point out about this result. First of all, you might be a little bit excited to see that because we've already confirmed in the Slinky lab that this in fact is the kind of experimental dependence that we see when investigating the magnetic field inside a Slinky. It has a linear dependence on the number of turns per unit length, and it has a linear dependence on the current that's going through the coil. Second, this thing is a really nice approximation of a strong, uniform magnetic field in that the magnetic field lines all point in the same direction, and the magnetic field has the same strength everywhere inside the solenoid. That's what the word uniform means, of course. And so this is sort of like the magnetic equivalent of a capacitor. Just as capacitors give you a very strong localized electric field between the charged plates, the solenoid gives you a strong localized field inside the coil. And just as with the capacitor examples with Gauss's theorem, the only thing influencing the field is the amount of the stuff, the current enclosed in this case, or the current that runs through the wire, I should say. Just as the strength of a capacitor depends only on the area distance ratio, which is sort of like turns per unit length, and the amount of charge density on the plates themselves.